All right, we are going to talk about diagonalizability, which is 5.2. Diagonalizability. All right, first we are going to see following example. So we say we have like linear transformation T, and we have lambda 1 v1 and lambda 2 v2. They're both eigenpairs of this T linear operator T, and we have another condition, lambda 1 is not equal to lambda 2, then we can prove that v1 and v2 is independent. So if you want to prove two vectors are independent, then you usually always look at this kind of equation and see if there's non-zero C1, C2 satisfying this. And if I take T both sides, like T of 0, then we know that T of 0 is always 0, and T can be separated, so T v1 and C2 T v2. That's what we can write. And this is lambda 1 v1 and lambda 2 v2, so C1 lambda 1 v1 and C2 lambda 2 v2 equals 0. And I'm going to relate 1 and 2 equations and then eliminate the second term. So I need to multiply lambda 2 here. So what we do is 1 times lambda 2 minus 2. Then we can get C1 lambda 2 minus lambda 1 v1, which is 0. And we know these two cannot be 0 because two eigenvalues are distinct. And v1 is not equal to 0 because this is eigenvector. So the only thing has to be 0 is C1 equals 0. And we can similarly prove C2 equals 0. So that proves independency of v1 and v2. So if you are taking one eigenvector from lambda 1, one eigenvector from lambda 2, from two distinct eigenvalues, then they are independent. And this can be generalized. So to generalize that, we're going to introduce eigenspace. So suppose lambda is eigenvalue of T, then its eigenspace is basically null space of T minus lambda I, which is, we call that eigenspace of lambda. So this is collection of all eigenvectors which corresponding to, associated to eigenvalue lambda. Now if we extend or generalize the previous example, and this can be written as this. So you have distinct eigenvectors eigenvalues of T, and you take independent eigenvalues from each eigenspace corresponding to lambda 1 lambda k. So let's say that is Si is E from E lambda I is a set of independent vectors. Then when you put them together, it automatically gives independent. Linearly independent. One direct application of this theorem is following. So this is another sufficient condition for diagonalizability. So if T has n distinct eigenvalue, then T is diagonalizable. Why is that true? Because from theorem 5.1, which is the very first theorem in this chapter, so in that theorem 5.1, if you recall, then if T has n many linearly independent eigenvectors, then it's diagonalizable, right? So this is the statement of theorem 5.1. Now, if you have n distinct eigenvalue, then we can choose one eigenvalue, one eigenvector from each eigenvalue. So let's say this is v1, vi from lambda I. Then put them together. So if you put them together, then they are independent by this lemma 5.4. So if you take one eigenvector from each eigenspace, then they are automatically independent. So by lemma 5.4, right? So that implies diagonalizability. Now, for further investigation, we need a new concept. So a polynomial f splits over f if f of x is a constant multiplied by x minus lambda 1, x minus lambda 2, could be many, x minus lambda k. Basically, it says it's a product of linear polynomial or degree 1 polynomials. So usually we talk about characteristic polynomial in linear algebra. So let's look at one example. So I am going to consider 0, 0, negative 1, 1. And this is very tricky concept because it depends on which field you're talking to. Usually, so far, most theorems works for no matter real number or complex number for the field, but this one is different. Diagonalizability makes difference for depending on which field you're talking to. So we are looking at its characteristic polynomial, which is determinant of negative lambda, negative 1, 1, which is lambda squared plus 1. We know that this is not factorizable but on R, but it is factorable on complex numbers. So our conclusion for this problem is that A, characteristic polynomial of A splits over C, but A not splits over R. I didn't write characteristic polynomial of. I will to simplify my writing or to save my writing, I omit this word, but it should be clear from the context. Now, the question is, why do we need this new concept, splits over f? how does it relate it to our diagonalizability? So the answer is following. A is diagonalizable, then A splits over F. In other words, splits is a necessary condition to diagonalizability, but not the other way around. I cannot say, yes, I cannot say if A splits, then it's diagonalizable. So the proof is, again, if A is diagonalizable, then you can always write this Q inverse lambda. Q lambda is diagonal. And then determinant of A can be simply written as determinant of the characteristic polynomial. It's A minus lambda I. Its determinant is determinant of lambda, big lambda, minus lambda I, which is, if I write lambda as lambda 1 to lambda n, right? So it's diagonal. Then this is lambda 1 minus lambda and lambda n minus lambda, which means it splits. So we go back to revisit this example 5.7. So we talked about A, 0, negative 1, 1, 0, right? So we know that A splits over C. And also we know that lambda 1 is I, lambda 2 equals negative I. We have, in C2 space, we have two distinct eigenvalues. So it's diagonalizable by example, yes. So this is sufficient condition. By example 5.6, if you have distinct eigenvalues and distinct eigenvalues. So this is example 5.6. Now again, A does not split over R. Then what can you say about that? From example 5.8, if A is diagonalizable, then A splits. But if A does not split, then A is not diagonalizable. So A is not diagonalizable by example 5.8. Yes. So if we, there are a couple of things we have to emphasize. So to the summary, diagonalizable means its characteristic polynomial splits. Then on the other hand, not splits means not diagonalizable, that's for sure. One question is, if characteristic polynomial splits, then is that diagonalizable? The answer is no. So here is the example we can use as counterexample. So if A is given by 1, 1, 0, 1, 2 by 2 matrix, then we know that its characteristic function is determinant of 1 minus lambda, 1 minus lambda, 1, 1, 1, 0. So this is 1 minus lambda square, which means splits. Even for R. However, we can see that its eigenspace is null space of A minus lambda I, which means 0, 1, 0, 0, which is, we can easily see this is span of 1, 0. It's dimension 1, so there's no way we can get two independent eigenvectors for A. So that means it's not diagonalizable by very basic fundamental theorem, theorem 5.1. So the deeper theory is following. So then what does it mean, or how the how a matrix related to splits? So here's the answer. A characteristic polynomial of A splits if and only if A is similar to upper triangular matrix, which means A is can be written as Q, U, Q inverse. U is upper triangular, not diagonal matrix. And to be similar to a diagonal matrix, then we need splits plus some condition. So that's the last theorem of today. Oh, right. Before that, we have to define multiplicity. So easily speaking, the multiplicity, suppose lambda, so here lambda equals 1 is eigenvalue, then its multiplicity is 2, which is the degree of this 1 minus lambda. So to define that, so suppose if lambda I is eigenvalue of T, then Mi is multiplicity, its multiplicity, if it's the largest integer such that lambda minus lambda 1, lambda I, Mi, divides its characteristic polynomial. So this is the definition. And we're going to describe the last theorem. Let's say T splits. We know if T splits, it guarantees similar to upper triangular. But then T is diagonalizable if and only if lambda I equals Mi for all I equals 1 to k. So here lambda I mi's are all available eigenvalues and multiplicity of this. Oh no, so it's not exact. Sorry. Maybe we can talk about this later. The dimension of eigenspace. Dimension of eigenspace. We stop here.